So now, Joseph, now,
Yes.
if you're ready, I will give the word to you.
Okay, thank you.
Great.
So I don't have slides for this. I just thought I would show you the tool. So over the past 3 months or so, Gang and I have been working on training settlement machines on FPGA. We haven't completed that yet, but as a byproduct, we came up with this tool, which I'll show you. We call this Matador. And basically, I will just walk you through what the functionalities are here, and as we go through it, you'll understand what it does. So the first thing we can do is open a manual for it. Okay, so if I zoom into the manual a little bit. Okay, so the main ideas here, you can train a model. So the full flow is you train a model, we generate RTL for it, and then you can synthesize it and implement it on an FPGA. And we support this pink flow where you can write Python code and interact with the hardware that you've generated. Alternatively, you can take a existing model from anywhere, it doesn't matter, and we will generate RTL for you and then also do the same flow. Or you can just use it to train the model. And we will go through all of these flows. So just about how we are connected at the moment, I have my laptop connected in a local network with my FPGA. And these are the boards that we support for this. Okay, so the first thing is setup. You'll need some sort of Ubuntu distribution, and you'll need to have installed Vivado. The free version is fine. Then let us go into setup. Okay. So now we need to specify the path for Vivado, which I will do here. Yes, that's fine. And then we will specify some output directory. So we can say demo test. That's fine. Okay, so now setup is complete. We will train a model. Okay, let me just show you what's happened so far. This is the Matador main file directory, and we created a user directory called demo test, which is here. And it has a config inside, which just points to Vivado. That's fine. Okay, so now we will train a model. Let's see, train. And we can specify something like the number of clauses. Matador comes with some data sets already, so you can have a look at, I think in here we have MNIST data, so we can use that. So clauses, I will do something relatively small so it trains within the time that we have. Anatoly, this is coalesced, so that's why, forgive me for a big T value, it's different. Let's say 20, okay, so that's fine. Now we have started training, and well, it may take a long time if you specify more, yes. So fine, let that one train. 8, yes. Okay, so let that train. In the meantime, I'll show you the other flow where we can import an existing model. Let's open another Matador. Okay. So this, unfortunately, you have to go through the setup stage again, so we will do that. And this time I will go into existing model trial. So existing model trial is also something in the directory where once you've trained the model, you will get these outputs, which are basically the TA states, the weights, and then a config file determining, it basically explains what the system was that was trained. And we're going to use this to generate some RTL now. So 1 second. I will point to this directory in my use existing model. Okay, that's fine. Now inside here we have the information. So if I open the second Matador, Vivado path. Sorry, 1 second. Made an error there. Let's try again. Okay. Then this one. Okay, now let's see. Yes, fine. So now we will go to generate RTL. We can specify, so here you see it's found our directory and we can convert the existing model. So if I go there, I select the TA file, the weights file, the clauses that I specified. Let's see here. Clauses was 500. Classes was 10. S value, bus width. Okay, I will come back to this. I have something else to show you once we've done this. 64, features 784, stages 4, sorry, states 400, stages 4, that's done. Okay, so now this will have outputted within that directory an RTL folder, inside which we will have the hardware code. So I would like to take a little detour to show you what it is that we've generated. So Gang and I prepared this for a competition for Xilinx. I'm going to show you very briefly some slides for it, not all of them. Okay, so the main thing is that TMs generate clause expressions. Matador basically takes the clause expressions and generates custom circuits. And the design looks a little bit like this, where data will come and it will be routed to one of these clause expression blocks. So for example, if your data is split into 64 bits, data 0 will go to the first block, which corresponds to the first 64 bits of the data from the clause. Then data 1 will come and it will go to the second one, and then data 2 will come, it will go to the third block, etc. And so now I can show you a little bit of what was generated. So here you see we have the clause expressions, and they have been split into, sorry, 1 second, let's try again. Yes, so these are the partial clause expressions, and they've been split into various different blocks. So we see here we have block 4, here we have block 5, as you saw in the slides, and it goes up to, let's see, block 12. So starting from block 0, that's 13 blocks. Okay, so that's fine. So far we have trained a model. Oh, let's see how the training is doing. So this is the how the training is happening so far. So here we have the training accuracy and the number of includes. We didn't choose hyperparameters very well, so this is why the training is behaving like this. But just to show you that you can train on here, we have generated RTL. Now let's go back to the manual. So the next thing we can do is synthesize and implement our design. We won't have enough time to actually do this fully, but we have some scripts that automates this process. So let us do that from this one. I will just run it and then close it because we can go through things we've prepared earlier. So the RTL is found, and if we wait a little bit, it will run Vivado, it will synthesize the design that we've created, and it will map it to the FPGA. So the outputs from this will be a bit stream that will be used to program the FPGA and a HWH file, which will describe the hardware, which is used for the Python libraries. So this, I will close actually. I will close the, that's fine. Okay, I'll close this one. So now we have covered the full flow for training the model, generating the RTL. I've shown a little bit of how the synthesis implementation happens. And then finally, we can talk about the pink flow. So once everything is done, you will get a directory that looks a little bit like, let's see. This one, a little bit like this. So here we have the TA that was trained, we have the RTL, which we saw before, and we have the generated files. And the outputs that we're interested in here are the bit stream, let's go back, the bit stream and the HWH file, which is these two here. If we press the pink button here, it should run a web page, which will run my Jupyter notebook, where we can load in the bitstream and the HWH file, and the user can write their own Python application to interact with the hardware. So hopefully that will happen. The FPGA is not turned on, my mistake. Just a little bit of time then. And, does anybody have any questions? Yeah.
So this HCB is hard-coded?
Hard-coded clause block, yeah.
How come you came at 13 number?
Okay, so MNIST has, I will show you. So MNIST has 784 features. The bus that connects a processor to the hardware is 64 bits. So
okay,
it's 13, yeah.
So 13 blocks.
That will be automated for however many features you choose. It will split accordingly.
IP address, we have to, so you directly clicked on pink and a window opened in this.
Yeah.
So we have to set that in our laptop.
So if you look in the manual, you need a setup like this. It doesn't matter what the IPs are. You just need to have a local network where you have static IP and the board has a static IP. That's it. Okay. Let's try again. Yes. No, it doesn't like. This is the only problem with the flow. This is not part of my design. This is. Yes, this is Xilinx. Let's see if we can ping it. Yes, we can. Yes, that's right. The AXI interface. Yes, okay, so it should be fine. We should be able to run it from here. I'm determined to get it from here. Yes. Okay, so let's just wait a little bit for the notebook to load. Okay. I prepared a little demonstration application earlier. Within it, our bitstream should be already loaded, so we will just wait for this. All in all, by the way, if you'd like to do this from beginning to end, it takes around 40 minutes for training the 500 clause MNIST, generating the hardware, and then running this application. So the first thing we will do is load the bitstream.
For those of you who didn't program
kernel error.
Writing something from scratch and then getting it with DAY2 and running on FPGA, you're looking at least 3 to 4 months of work. Meaning, resolve this.
Okay. No. So the notebook is running on the FPGA actually. Yes. Okay. So now we're in business. The bitstream is being put onto the FPGA. Yes. So we will wait a little bit. This has a little bit of waiting time, so I will just roughly explain to you what each of these things are doing. First, we've loaded the bit stream, and we also have the HWH file within the directory that this application is running in. Next, I will just query you what we have created. So this is a dictionary of all of the hardware components in the system. So this is why the pink library is nice, because you can, before you would have to go through and find the specific C functions in order to access registers. But here it's all a dictionary, and you can just get the right string and you can access whatever register you need. So now I will initialize the channel for transferring data. So that's done. The next thing is I have some test data for MNIST. It has 9,999 values. We're going to pack it into bits, and we're going to send it to the hardware that we've created. This takes a little bit of time, so please bear with me.
So 1 million
around 10,000, right? So what is happening here is I have 784 features, and then I'm dividing them into 64-bit packets, and those packets will be sent to the hardware to interact with the appropriate clause block. So we will just wait until this is done. While that's happening, I want to show you how we compare once we get some comparisons. Yes, yeah, that's very true. Right. Yes.
We have all 784 at the same time.
Well, 64 at a time.
So it's
when you actually run them through
oh yes, all at the same time. That's right. Yeah. So we were inspired from this work from Xilinx, where they did a similar thing with BNNs, and I would like to show you how we compare against the fastest BNN.
Tausif, but I think it is pipelined, right? The first 64-bit packet comes and it computes the partial sum for that 64-bit. Then the next 64, right?
It can't be pipelined because it's one-to-one, you see. That's one disadvantage of this.
So you wait for all 13 packets and then you start.
Yes.
So you go wagging tail, like you get 64, bang, 64, yeah. But you can't feed from the first 64. It's not.
For reference, the fastest BNN that Xilinx gave that performs MNIST ran at 200 megahertz. It had LUT count of this. This was the BRAMs that we used, and this is the latency that they had. Let's see, we should get something similar actually. Okay, this is done. Let's run the inference. I think it's this one, yes. Yes, okay, so it's complete. Ignore this, Gang and I were just doing some debugging, but here, okay. This is the data point number. This is the classification for MNIST. And at the end, we will have our execution time, which is here. So let's see how well we did. 0.0043 divided by, which is this, times by 10 to the 6. 0.43 microseconds. So that is a little bit slower than this, but now I think we should look at LUTs and power. So let's open up what we generated. Yes. And let's look at LUTs. Okay, so our design has 39,906 LUTs. So it's less than half basically of this. We are running at 50 megahertz. So, yes, okay, let's look at power. Yes, 200 megahertz they were running. So this is our on-chip power, 1.467. watts versus 7.3 watts. So I can show you one more interesting thing about Matador as well, if we have time. A little bit. Very quick. Oh, okay. Let's see if we can do this quickly. Okay. So Matador, the one that we've created, we were using it for refining a design. So we were going through these steps multiple times. So as a result, it has debug capabilities for the AXI interface. So I can show you that. That you can also use to determine exactly how many clock cycles it takes for you to do a classification, which we should be able to see. Didn't start, okay. Should yes, it should be this directory. Basically, I'm going to open the design that we just created. Sorry, 1 second. The design is within the stage. This one, hard-coded LA inference. All right. So we have it open already. Okay. Open projects. This one. Okay, so if we open this. So there is a logic analyzer that we use to poll certain ports, and we can use it for seeing how the transactions happen, and we can see it for how long it takes in clock cycles for classification. So I will just run a trigger. I think that trigger is fine. Run this. Okay, so now we're waiting, and I'm going to run the inference again. Let's see. Okay, so we will wait for this to finish. Okay, that's fine. Now we have some data. Okay, so just to show you what is happening, let's zoom in a little bit. Okay, so this stream is the data coming in. This stream is the classifications going out. So here is this classification 7, 8, 9, 0, etc. And clock cycles, did we add clock to this one? Okay, I didn't pull clock. I think this one we were using just for debugging AXI stream, but it can be used to get, right, it should be 13 actually. Yeah, it should be. Yeah, so yeah, that's it. If you would like to use it, it is open source, but I showed you from the development branch and I will push changes soon. That's it. Thank you.
Very cool. Impressive. So we don't have time for questions. So is there any questions? Okay, I have a quick one. How would this be possible to have this in TeamU as well? If we made this C code and as you suggested, could we do this in
yes,
with TeamU?
it should work. Yes.
Awesome. Yes. Then
right.
Yeah. Okay. Yeah.
Yes.
Nice. Yes. Thanks.
Okay.